This module consists of this module consists of chapter 3 and chapter 4 of the textbook. I combined two chapters and made one module. Chapter 3 is about construction of semiconductor devices. Chapter 3 is about construction. Construction mechanism of semiconductor devices. And then chapter 4 is about actual application of semiconductor devices. So here we will talk about diode. Diode is the first semiconductor device that we are going to study. And that is the basis for transistors, metal oxide semiconductor that people use these days for building CPUs, making CPUs. So very, very important model that we are entering. So the construction mechanism, I'm going to do it later because of the laboratory experiment. I am going to directly talk about diode for the moment. So diode is the first nonlinear element that we are studying. It is the first nonlinear element. Why it is nonlinear? For resistor, inductor, capacitor, these are linear components. These are linear components, which means that V is proportional to I, or I is proportional to V. Voltage current relationship is proportional. Voltage and current relationship is proportional for these devices. For these devices, voltage current relationship is proportional, but the first nonlinear device that we are starting to talk about is called diode. It is nonlinear. It is nonlinear because I V characteristics is nonlinear. So this is a nonlinear function. This is a nonlinear function. So voltage and current relationship is nonlinear. For resistance, if we increase voltage, current is going to be more. Current will be increased. If we decrease voltage, current will be decreased. Okay? But it is the relationship is linear. Relationship is simply a straight line. For IV characteristics, for resistance, inductor, capacitor, relationship is linear. But for a nonlinear device, the diode that we are talking about, IV characteristics is not linear. So it is going to be, if the voltage, if y-axis is I and x-axis is V, IV characteristics is going to be like that, nonlinear. The diode that we will be working with, it's a two-terminal device. It's a two-terminal device. That means it has two legs, two terminals, two legs. It's a two-terminal device and enables AC signal to DC signal conversion. It is used to convert AC signal to DC signal. It is used for logic operation. It is used, they are used for switching, on-off switching. So you will be using mechanical switch just to have an idea in the coming lab. But just to have an idea, but actual switching, like logic 1, logic 0, they are actually implemented using semiconductor devices. Logic 1, logic 0, you guys learned in ECE 102 digital systems, where you learned about Boolean expression, Boolean algebra. You have seen the truth table 1, 0, 1, 0. These are just on-off, basically. You can simply think of on-off signals. And these on-off signals are actually implemented using semiconductor devices. Put it in a circuit using semiconductor devices, and these on-off signals are actually implemented using semiconductor devices. And these are, this diode is the foundation of BJT, bipolar junction transistor, and field effect transistor that we will be studying in module 4 and module 5. So, in this chapter, in this module, we shall study ideal diode model, and you will see actual diode model in PSpice. You will see actual diode model in PSpice. And then we would be learning silicon junction diode, the devices, the semiconductor device that is basically made using silicon materials. And its terminal characteristics, IV characteristics. We are going to analyze diode circuits and key diode applications in power conversion and signal processing. Here, I'm not going to read my slides, but here a bunch of applications that you have. You must have heard about voltage regulation. Voltage regulator, 5-volt voltage regulator that you see, okay? And also, you see you have like DC voltage regulator, you plug it in, for example, in AC, and you get constant DC signal. So you have DC voltage regulation. These are basically application of diode. These circuits are implemented using semiconductor devices called diode. Rectification is used to convert AC signal, the wall voltage, which is AC, to DC. So AC to DC conversion is performed using diode. So the other applications that I'm not going to read, but in this lab, in the coming lab, we are going to implement this rectification, AC to DC. Clear? In the coming lab, we are going to have this rectification, AC to DC. Here I have a nice little diagram. So we are going to start with ideal version of diode. You will see what is ideal version of diode. And then from ideal we go to real diode. So we do take into account the mathematical properties of diode, characteristics of diode. We do take into account the actual behavior, okay, instead of considering the ideal version. We can build the circuit using ideal version of the diode, and we can build the circuit using ideal version of the diode, and then we can actually analyze these BJT bipolar junction transistor, field effect transistors. We can actually analyze these circuits using diode characteristics, diode circuit. Just if we understand diode circuit very well, analyzing circuits using transistors will be simplified. would be easy. And we can also take into account the real diode function that takes actual model, and actual model can be used to analyze BJT and transistors, BJT and FET. So let's talk about ideal diode. Okay. So a diode has two terminals. These two terminals using this diode. Okay, now it looks like this one. You'll be using this diode we have in the lab. So do you see it has a little band in one side, and in other side you do not see any band. This band side is called cathode side, and without band, it is the anode side. And this is basically just the symbol. This is basically just the symbol. The current flowing through this diode is denoted with I, and the voltage across diode is denoted with V. Of course, as I said, that the voltage current relationship is going to be nonlinear for axial diode. The voltage current relationship is going to be nonlinear. Now, what is the ultimate goal of the diode? Diode is a semiconductor device that allows current to flow in one direction only. Diode is a semiconductor device that allows current to flow in one direction only, not in other direction. Diode is a semiconductor device that allows current to flow in one direction only, from anode to cathode. So diode allows current in one direction. And since I said that diode allows current to flow in one direction only, from anode to cathode, so this mode is called forward bias. And I have this in the next slide. And this is called forward bias. Forward bias operation. Okay? Current cannot flow from cathode to anode. And this is called reverse. No conduction in reverse direction. No conduction in reverse. Ideally, no conduction in reverse bias. Only current can flow in one direction. Now, diode is basically the basic nonlinear device for rectification and switching. Switching means just on or off, and you will see in a moment what does it mean. Okay. If this voltage, guys, we have this voltage, the voltage here, anode to cathode, so we have, you can just think of this as a voltage source. V, voltage of anode with respect to cathode. Make sure guys you understand. It's very important because you will be dealing with bridge rectifier, and it's very important. So voltage of anode with respect to cathode, which means that if you take a voltmeter and negative terminal of the voltmeter is at the cathode leg, and the positive terminal of the voltmeter is the anode. So if you get positive voltage, which means if we have positive voltage, V is greater than 0. Okay, so if you have positive voltage, so this diode, can actually, you can actually replace this diode with a piece of this is anode, this is cathode. You can just think of this diode as a piece of wire. If this voltage is positive, V is positive, which means anode voltage is positive with respect to cathode voltage, which means that you can just think of this as a piece of wire. That's it. Simply a piece of wire, which means that the diode is on. Which means diode is on. If the voltage of anode terminal is positive with respect to cathode terminal, you can think of this diode. Just think of this diode as a piece of wire. That's it. If the voltage is negative, which means that this V, if we have a voltmeter and positive terminal of the voltmeter is at the anode terminal and negative terminal is at the cathode terminal. Now look at the voltmeter. If you see it's a negative voltage, if you apply negative voltage, that means it is in reverse bias condition, and you can just think of this diode as an open circuit. Nothing but just simply open. So that is the reverse bias condition. So equivalent circuit, so you can think of this diode in the equivalent circuit as such. So equivalent circuit, so we just put it in the form of the voltage, current and wires. So we have anode, cathode, this is simply open circuit and no current will flow. I is going to be 0 and reverse bias V is going to be less than 0. So which means diode is on. In forward bias, V has to be positive and then diode is going to be on. We said the diode is on and 0 voltage drop. Voltage between these two terminals is going to be 0, which means it's a piece of wire. Graphically, this IV characteristics we can graphically show that this is when V is negative, no current will flow, which means that the current is going to be 0. When you have V positive, ideal version, I'm talking about ideal version. So when you see V positive, you see that there is no resistance or anything. If we apply some voltage, V is positive, you see drastically this current is going to be dead, infinite, ideal. So this portion is the reverse bias, this portion is the forward bias. Here, current flows when V greater than 0, no current when V less than 0, and sharp nonlinearity at origin. Sharp nonlinearity at origin here. This is nonlinear. You cannot. It's highly nonlinear. Now, let's take a moment to think about connecting resistance over time. Here, forward bias diode means that we have DC power supply in our lab. So here you apply DC power supply, positive, negative. So let's say 10 volts here. Now this positive you apply here. So in short, because it's a bit advanced course, it's not basic circuit theory that you learned in 204 or 100. So that's why in almost all the circuit diagrams you will see that author has denoted power supply just like that. Okay, instead of the power supply that I'm providing. So when it is plus 10 volt means that connection is like that. So you have positive terminal and you have negative terminal. Positive terminal you apply to one end of the resistor and negative terminal you apply to the cathode terminal of this diode. Okay. So now when because positive terminal you applied to the resistance, and this resistance is connected to the anode, and negative terminal is right here, you will see this voltage is going to be positive. This voltage is going to be positive, and this diode, of course we are considering ideal diode. So because that the anode voltage is greater than cathode voltage, therefore this diode, you can just think of this diode as a piece of wire. So piece of wire, which means that the voltage between these two terminals is going to be 0 volt. Now the current here will not be infinity here. Even though the diode is ideal, that the current is not going to be infinity. Why? It's because of the resistance connected in series. Because of this resistance connected in series. So therefore, the current is not going to be infinite. If we simply apply voltage without resistance, then current is going to be infinity, because diode will act as a piece of wire. Current is going to be infinity. Now the current is limited by these resistances.
So if you did that in reality, would you try the diode? Like,
Or you will not try. Of course, there will be some resistance practically. There is some resistance practically, but there will be high current. It's going to be very hot. It's going to be very, very hot. Okay. All right. So here, because it's a piece of wire, you can just think of that the current flowing through this resistance is going to be voltage, which is 10 volt. It's 10 volt over 1 kilo ohm resistance. So it is going to be 10 milliampere current. So 10 milliampere current will flow through this diode. So here diode is on because the anode voltage is going to be positive with respect to the cathode voltage, or you can say anode voltage is more than the cathode voltage, and external resistor limits current to 10 ampere, and diode voltage VD is approximately 0 for ideal case. Now let's think of this reverse bias condition. So again, so this 10 volt, you can think of this as positive here, negative here. This is 10 volt. Now, anode terminal of the diode has less voltage with respect to the cathode, because here we have positive 10, here we have positive 10 volt. So cathode voltage is more than anode voltage. If cathode voltage is more than anode voltage, which means that the diode is on. So you can just think of you can simply think of this diode. Nothing here. It's an open circuit. So actually I made a typo here. It is not going to be 0 volt. It is going to be, we apply here. If you have a voltmeter right here, you will see this 10 volt.
What was that square?
It wasn't a typo, it was just coming up with that.
Oh, it was not right. Oh, there you go. There you go. I just covered it up. Okay. All right. Good job. So it is 10 volt. So you have, if you have a voltmeter here and here, you will see that it's going to be 10 volt. And you can think of this as an open circuit. So here, cathode voltage is more than anode voltage. That's why it is reverse bias. and it is going to be on. So we say that diode is off, reverse bias, and resistor limits the reverse bias voltage to 10 volt, and diode current, this diode current is going to be 0 milliamp. So here I have a remark, resistor plays a crucial role in said diode operation in both. Now this is one part of the lab. The theory that I'm going to cover here is going to be one part of the lab. So we are taking off an ideal diode. Still, we are considering ideal diode. What it means, ideal diode, what it means that if the anode voltage is greater than cathode voltage, we can just replace diode with a piece of wire, and the voltage difference between diode's anode terminal and cathode terminal is going to be zero. And if the anode voltage is less than the cathode voltage, okay, then diode is a reverse bias condition, and we can think of diode as an open circuit. So still, we are in ideal mode. We are considering ideal diode. And rectifier circuit is basically converts the AC to DC. This is the first step of conversion. Of course, like once you have laptop charger, right? So you have a laptop charger, you plug it in on 1 voltage, it's a 120 volt, it's an AC voltage, okay? But your laptop is taking 12 volt DC. Of course, you will see inside this adapter, you have complex circuit here. But how does it do it? This is the first step of converting. Rectifier, half-wave rectifier. So you see that what it does. So consider the rectifier circuit below. Again, this rectifier circuit are in the first step of converting AC to DC. So we apply positive voltage here. We apply positive voltage here. Therefore, anode voltage is going to be more than the cathode voltage, and we have the voltage between these two terminals denoted with VD. So the VD is going to be 0 in forward bias because this voltage is going to be more than this voltage. And we have scope, oscilloscope, we take output across this resistor. So when input voltage VI is positive, diode conducts. So the diode is going to be a piece of wire. So you can just think of this as a piece of wire. Current ID is going to flow, and this current is going to be limited by this resistance. So diode conducts. If VD equals 0, output voltage. Okay, you tell me what is the output voltage now? V sub I. We have the input voltage. So here we have more voltage than anode is the voltage diode is on. So you can think of this as a piece of wire. Now you tell me what is the voltage across this arm. It's only one resistance connected. Simply VI. Okay. And the current is going to be greater than 0 because this current is going to be greater. Some current will flow, but the current is going to be limited by the resistance. So the current is going to be ID is going to be V out over R, which is same as V out over V sub I. So some current will flow through this resistance. Now we have reverse bias mode. So we have input voltage here. Now we say that input voltage, so this voltage is less than this voltage. The voltage of anode terminal is less than the voltage of cathode terminal. In other words, voltage of anode terminal with respect to cathode terminal is negative. If that is the case, then diode is simply an open circuit. There is no connection. There is no connection. ID is going to be 0. So because no current is flowing, because it is an open circuit, no current will flow through this resistor. So the voltage VO is going to be R times ID. Because ID is 0, so therefore output voltage is going to be 0. So if this voltage is negative, diode is off. It's an open circuit. So ID is going to be 0 and VD is going to be negative. So the output is going to be 0. So no current will flow. Now think of this VI as, if I have VI, so VI is the sinusoidal signal. If this is VI, so now take the output. You apply sinusoidal signal to the input. What will be the output? When you have positive input, so this is positive with respect to anode, so therefore diode is going to be on. Whatever voltage you have is going to be appear across R. So therefore you have whenever input is positive, output is going to be exactly the same as you said. Whenever input is positive, output is going to be same as input. So the output is going to be same as input. Output is going to be same as input. And then when you have this voltage negative with respect to this terminal, negative. So therefore, this voltage is going to be negative with respect to cathode terminal. So therefore, diode is going to be off and output voltage is going to be simply 0. So that's why the output voltage is going to be 0. So you can just put it on oscilloscope, you will see that the output voltage is going to be 0. And then same thing, when input voltage is positive, it is going to be same as the output is going to be same as the input. And as soon as input goes to negative, the output is going to be 0. You see that? So we are basically clipping the input signal and we are just keeping just the positive portion of the signal, not the negative portion. Negative portion is basically executed by the diode. Diode is not letting anything pass when the input voltage, anode voltage is less than the cathode voltage. So I'm going to stop right here, the theory. Now I'm going to move on to the laboratory handout. This laboratory handout, I modified slightly. Still, I'm going to modify from my laboratory book that I used for some other courses. Here, So mechanical switches, LEDs, voltage rectifiers. We have two types of diodes. You can use 5817 or 141 48 diodes. And you don't need double pole, double through switches. How do they work? I'm going to talk about it in a moment. So these are all the parts that you need. Mechanical switch that you will see. You will be given mechanical switches, and that those are double pole, double through switches that you will see. So you have like in the lab you will see that you have two sides, and in one side you see 1, 2, and then you have different colors, and another side you will see another side you will see this color, and then you will have this color. Okay? So here this is basically DP, DT, double pole, double throw switch. So I did mention here, you will have to read double pole, double throw switch, which means that the double input, two output we have. So we have two sides here. Our previous laboratory director, he made these switches. So now we have two inputs, and each input is connected to two different outputs like that. So each input is connected to two different inputs. When if you flip the switch, so this wiper is going to connect to this terminal. If you flip the switch the other way, this wiper is connected to this output. You see that? And that's the internal structure of this mechanical switch. So for this side, again, if you have switch in one direction, this terminal is connected to, for example, output this wire, or if you switch in other direction, you will see this wiper is connected to this wire. So it is double pole, double throw switch, the switch that you'll be using. Diode. Again, here I also have a little bit of theory here. Anode and cathode terminal. The application is very similar to the diode concept. So you will be using LEDs, light emitting diode. Light emitting diode, here you have anode terminal, cathode terminal. The difference between a diode and this LED is that this LED, when current flows, you see light emits. When current flows, light emits. Now we have some LEDs in the lab as well. Very similar operating principle, very similar to the diode. Of course, now here it comes to Robin's question that in case if you do not put any resistance in series, high current will flow and this will burn the LED. Okay, so you have to put a resistance in series. Working with the LEDs here, first thing you will see flashing red light. So you will have a red LED and you connect with the resistance, and here you generate square wave signal. Square wave signal, and look at the pattern of LED. So you now understand the operating principle of the diode. LED is different, it's a little bit different, same operating principle, but it's a little bit different than diode because it emits light. You will need to implement this traffic light controller here using just mechanical switches. So you have north-south and east-west. So you implement this figure 6. So you apply some DC voltage, and you have you have one double through switches, you will see in one direction, green will be on, and the other direction, red will be on. So if you have switches in the same direction, okay? So if you flip the switch, you will see that here green is going to be in north-south, green is going to be on, and east-west, red is going to be on. So this is the simple circuit diagram. I do not have yellow. Even though I have the circuit diagram, but I just want you to implement this simple circuit that just gives red and green LEDs, that's all, using mechanical switches. And mechanical switches, LEDs, and voltage source. And then voltage converter. Okay, you do not need to implement this. So this is a little bit more complex. You need more switches, but you will be able to implement this if you understand the first one. But you do not have to. You do not. I did not. Again, I'm still modifying my book, and I'm writing as I go. So I did not have description for this. Okay, but you understand clearly what this is. So voltage converter using diode. What you do, you apply sine wave here, and then you have a diode in series, and here you take the voltage across the diode. So you will see, actually you will see the output should look like this. Output should look like this. Okay? So how to rectify? So I went through the operating principle in class already, and this one is the full bridge rectifier. Okay, so full bridge rectifier, I will go over the theory in class. I did not go over the theory, but you know the basics of diode. You just construct this diode. You will see. I will talk a little bit about it in class one in the lab session on Thursday as well. So how it works, and the output, if you see the output across this resistor, output is going to be look like this. So you are basically preserving both positive and negative cycles. So now you are gradually seeing that it's in the first circuit, you are rectifying the half wave. Here you are rectifying the full wave. So the output will look like this. Now here, when you take the output across this resistor, now you guys tell me that in 221 or in 240, did you guys use math channel in oscilloscope? Math channel. Exactly once. So you will need to use math channel to get, I will show you how to do that. The math channel to get the voltage difference between these two terminals. So you will have to use math channel. You have one channel right here. So you need one channel. Use channel 1 for this input, channel 2 for this terminal, and for this terminal you use channel 3. So using math channel, you should be able to subtract channel 2 minus channel 3. Channel 2 minus channel 3. You use math channel. Okay. So then you see this output, and it perfectly works. We tested it for many years since I started writing this laboratory handbook in 2017. So I actually have ME students implement this method as well. So it works. Okay. It should be a piece of cake for you guys. Now we have a little bit of theory that the average voltage. We went through how to compute average voltage, and then average voltage for half wave rectifier. Average voltage for half wave rectifier, which means that if you see the output like that, average is going to be This is the average voltage. Okay, and this average voltage, if you actually use DC voltmeter, if you use DC voltmeter across the resistor, it is going to show you the average voltage. DC voltmeter, it is going to show you the average voltage, and this average voltage is mathematically computed as such for half-wave rectifier, and for four-wave rectifier, it is going to be double. For four-wave rectifier, it is going to be double. Now for the pre-lab, guys, here I'm asking you, this is just a sketching, okay? Figure 4, you go to figure 4 and see what should be the output. Because you are passing this through an LED, you are passing a square wave through an LED, what should be the, how the output should be. You sketch that. And then this part for my, when I taught 100, EC 100 or also, when I, actually not 100, when I taught EC 204, now EC 204 doesn't exist, long time ago it's 240 now. When I taught this, and also when I, still I'm teaching EC 227 for ME students, I do not require them to use any circuit simulator, just MATLAB, okay? So here, I do not have anywhere that it's PSpice, but what you do, the requirement here is that you go to figure 8, this figure 8, draw this figure in PSpice, okay? Okay, draw this figure in PSpice, and then you have input, you see the output. Output should look like this, and that is the requirement, that is 15 points. Okay? Yes?
What libraries do I need to implement and what diode should I use for PSpice?
Yeah, that's what you need to do a little bit of research. Okay? So I showed you how to get the, if you look at the options, you will see PSpice model, and you should see some diodes here. I would like you to just explore a little bit, and I'll be there on Thursday, okay? I will help you as well. But you guys do a little bit of research, how to find the library for diode, okay? Okay? So TAs will be there, I will be there, who will help you. If you cannot find, we are there to help. Okay? So you draw figure number 8 in PSpice, apply this input with resistance 10K and show the output in PSpice. And it should be like half-wave rectified version of the input. So if you can show that part, you just include that output in the lab report, and if you can just simply show, that is going to be 15 points. Okay, and this MATLAB part, you guys work with MATLAB in 221, like 206 or not 221. So which course you learn MATLAB?
This year.
No, we did not have any MATLAB course before.
MATLAB is not touched officially in any courses this semester.
Okay, so actually this course practically is aimed for PSpice, like circuit simulator, professional circuit simulators. So I cannot actually focus on MATLAB, but I will be focusing on circuit simulator. But just for learning purpose, what we can do, I can spend some time, even I can show you my code. Okay, I can spend some time on Thursday and show you how to implement this using MATLAB. Okay, you can write during the lab you can write code with me, and you can work. Okay. That should not take much time. So that is just 20 minutes from your not previous, not from the course in the previous semester, but you said that this semester you are taking some MATLAB course. So yeah, I'll give you a little bit of base on MATLAB so that you guys learn. MATLAB Simulink, you cannot, as an electrical engineer, you cannot prepare a MATLAB Simulink. You have to learn MATLAB Simulink. Like these days, in many companies, you don't have to write code completely from scratch. Code can be generated automatically. There are some, modeling software, for example, Simulink. You just drag and drop those building blocks. You drag and drop the graphical programming, simply. But you will have to understand the input and output, what's going on inside. After that, you don't have to write code from scratch. You can just use the building block. You guys know what I'm trying to say, okay? So I'll just give you a little bit of hint on Thursday. So let's start with that, and then start with pre-lab. Okay, you go pre-lab, and we'll be taking it. Okay, and then finally lab work. You can we have diodes. You can start lab work on Thursday. If you cannot finish, you have one way to come to the lab. Anytime you come to the lab, and you can show the demo to the TAs. Okay?
When does the pre-lab due?
When?
Yeah.
Yeah, pre-lab, I made it due like in the following October 16th. Okay? October 16th. So if you cannot show, even if you cannot show pre-lab on Thursday, because Thursday you will be simply working on the lab. If you cannot finish the pre-lab, it's okay that you can show the pre-lab with the lab. Okay? But you will have to do it. Okay, so we have part 1, and then we have part 2, part 3. Part 3 is about half-wave rectifier, and part 4 is the full base rectifier. So you do need 4 diodes and 1 resistor. And you will see what output you see on the screen. So I want you to sketch that output. And when you write the reports, guys, some of you actually did for our first op-amp experiment, some of you did. In our laboratory computer, actually in almost all the laboratory computers, you will see there is a software called Open Choice Test. Using Open Choice Desktop, what it does, you can actually extract the plot that you see on the scope right in your computer. Okay? And you can paste that plot. You can modify a little bit, for example, background. You can do a little bit modification, and you can paste that oscilloscope plot in your lab. Okay? So that looks nice. The average voltage, you will be able to compute the average voltage. Your output is going to look like this. Of course, the average voltage for this output is going to be more than double, twice as you see in half-wave rectifier. So the average voltage is going to be somewhere Clear? And these average voltage, we have the formula. The average voltage is going to be 2 PS over pi. Okay, this is the computed version. You can actually see this formula right here. 2 PS over pi. This is the average voltage. And then you can measure this average voltage, which means that positive. So this is your full wave rectifier circuit. You can actually have a voltmeter right here. Positive, negative. The voltmeter here. So if you use a DC voltmeter right here, this DC voltmeter will give you the average. This DC voltmeter will give you the average voltage. And you have measured average voltage and you have the computed average voltage. So there should be. Okay? There should be. So that's all about the lab. Again, this coming Thursday, pre-lab, you can do pre-lab during the lab session. So it's going to be entire, just laboratory work. If you can show the pre-lab on Thursday, so we'll record it. If you cannot show, you can actually show the pre-lab with the demo. Okay? And entire lab report is going to be due on October 16th. Okay? Any questions, guys? No? Is everything clear? Yes.
Are we gonna be able to see our news, like what we got wrong on the?
Oh, yeah, okay, that's a good question. Yes, exams, they are in my office, guys. I don't return the exam to you guys, but you can always, you have the solution, but you can always just shoot me an email and come and see your exam copy. Clear? Yes.